All right, so today we're going to be using Desmos. So if you want to open it up on your phone or borrow a complete computer, please do that now. All right, so the key concepts here. So we're going to be talking about reciprocal functions. So I'm going to talk a little bit about why we call them reciprocal functions. So if you think of the regular function y equals x, that's just a standard linear function that goes through the origin. But reciprocal is when we flip a fraction. So technically x over 1 would flip to 1 over x. And this is how it looks when we do that. And the reason that it exists this way, and it has these two asymptotes, both vertical and horizontal, is because when we get to the point where we have an x in the denominator, we have restrictions on that x, okay? And we also have restrictions on that y. So whatever restriction on the x exists also affects a restriction on the y as well, because they're connected, right? One is dependent of the other. So this is the general form for a transformation of this type of function. In this class by now, you should all be familiar with the letters a, h, and k, right? You've seen this numerous times. Logarithmic, exponential, cubic, everything we've done, we always use these letters. And these always represent the same types of four transformations that can really happen. We know that a can be stretched, compressed, and if it's negative, it can be a reflection, okay? And then we also know that h does horizontal shifts and k affects my vertical shifts. And we know that h is also special because it's always the opposite of how it appears, right? Now with these particular functions, these are always going to be your domain. But keep in mind, h is always the opposite as what it appears in the equation. So if it's plus 4, it's really a negative 4 as h. Okay, so just always keep that in mind when you go through. That's probably one of the most common mistakes I see students make. So what the domain and range mean is the graph exists on all values for x except for whatever h is. So this is a way of me excluding h. We go all the way from negative infinity until we get to whatever that restriction is, in this case 0, and then the graph picks back up after 0 and continues on. Same with the range. It goes all the way from negative infinity up until we get to whatever that asymptote is, and then it picks up after the asymptote. Okay? So that's why we have those asymptotes there. That's the reasoning for them. And then lastly, end behavior. The cool thing about this, and this should be a little plus sign. I realized I wrote the same exact one twice. So make this into a plus sign right there. The cool thing about end behavior for these functions is it's always whatever k is. Because what you're going to notice is as the graph goes to the negative infinity direction, your graph is always going to approach whatever that asymptote is, which is k, that vertical or the horizontal asymptote. And then as your graph goes on this side, it's always going to approach k as well. So see how both sides of the graph get close and close to k. So let's go ahead and look at an example. And before we do that, I forgot to fill this last part in. Translations, h is always opposite. That's what that line should say. I'm going to write it in a second. My inner right tablet is loading. And there we go. Okay. H is always opposite. And k is always the same as it appears. But you all should be pretty familiar with that by now, right? All right. So let's go ahead and look at an example. Here's the steps for graphing. I don't need to read through these to you because we're going to just do it as we go. But this is a good reference point if you ever get stuck and you're working on a problem on a test or something like that. So I'm going to zoom in here so you can get a better look. First thing you want to do is let's look at this and compare it to the parent function. So I'm just going to write the parent function here so you can get a visual comparison. What is the only thing that's changed from the parent function? 1. The 1 changed to an 8. So what letter does that represent? A, H, or K?
H.
A.
Oh, A.
Because you see here how this is the one on the top is A. So that represents either a vertical stretch, a vertical compression, and or a reflection, right? So which one of these is that going to be? If it's greater than 1, it's a vertical
stretch.
Good. So the only transformation on this particular graph is a vertical stretch of a factor of 8. And if it were negative, it would also be a reflection, but it's not. So there's no reflection occurring here. Now we're going to talk a little bit about the horizontal and vertical asymptotes. We know that horizontal asymptotes are always represented by y equals k. Okay? So what is the k in this graph? So k is always what's added on to the end.
Oh, 0.
Since there's nothing there, it's just k is 0. So it's just y equals 0. And then to find the vertical asymptote, what you do is you set the denominator of your fraction equal to 0. So if I set x equal to 0, it's just x equals 0, right? Sometimes there's going to be something to solve, but this particular one doesn't have anything to solve. So if it were like x minus 3, you would then solve for x. Does that make sense? Okay. So now we're going to do domain and range. Domain is always based on h, and range is always based on k. So it's the same exact procedure every time. Negative infinity to whatever your h is, since we don't have anything added or subtracted to x, it's just 0. Union, 0 to positive infinity. And then my k is also 0, so my domain and range happen to be the same. But that won't always be the case. So that's just me following the rules on the previous slide. And for intercepts, I'll talk a little bit about how we can find those using Desmos, which is a little bit easier. Now, end behavior is always going to k on both sides. So, make that a positive. What is k? 0. So it's just going to be approaching 0 on both sides. So now that we've done that, the first thing I want to do is graph my intercepts. I'm sorry, not my intercepts. I want to graph my asymptotes. So I'm going to scroll over to my graph here, and I'm going to graph in those asymptotes. So I have one here and here. They won't always be on the origin. You'll see examples that aren't. This represents x equals 0, the line x equals 0, and this represents the line y equals 0. Okay? So once we get to this point, I'm going to pull over my Desmos screen so you can all see what I'm going to do here.
Can you move back over to the I missed the one x or y intercept. Never mind that.
We haven't done it yet. But yeah, we will get to it. It's easier to do once you have the graph. So I'm going to graph the function. To do that, I just use the division symbol. And then I'm also going to graph my two intercepts. I keep saying intercepts, asymptotes. So you should visually be able to see that these are the asymptotes because you're going to see that the graph is where they bend around. Does everybody see how the graph bends around those asymptotes? So if I would have accidentally typed in like a 4 here, you can tell that's not right. So you can always visually confirm that your asymptotes are correct using the graph. Does everybody see that, what I mean by that? Okay. So now that we have this, first thing we want to look for is intercepts. Does either part of this graph in the purple cross the x-axis or the y-axis at all? No. And we can tell that because if my two intercepts are the axes themselves, my two asymptotes, are we ever going to cross the asymptotes? No. So for that reason, we don't have, it does not exist for both of them. Okay? Neither of them exist. And say you want to define this algebraically. Okay? So algebraically, to find an x-intercept, I would plug in 0 for y. Algebraically, to find a y-intercept, I would plug in 0 for x. So if I were to solve this first equation, I would put this over 1, and I would cross multiply, right? What is 0 times x?
0.
What's 1 times 8?
8.
Is 0 equal to 8? This is a bad equation. Okay, it doesn't work. Now here, if I were to solve, what would happen in the calculator if I put 8 divided by 0?
You get an error.
I would get an error. So for that reason, see, this is why they don't exist algebraically, is the algebra doesn't work as well. So now going ahead and looking at our graph, let's go ahead and graph some points. So I'm going to pull up the Desmos. So the first thing I do is I hit this little gear button, and then I click that table button for that function. And that's going to give me the most standard table value of -2, -1, 0, 1, and 2. But realistically, you can put any values in here that you want, and you can add additional ones as well. So say I want to add another one, say I want to put in a 3, I can do that. I just hit enter, and I can add an additional one, or I can change the existing ones, and that just gives me the inputs and outputs of my function, and you can use those as we go to change up and figure out what's going to be useful to us. I'm going to change this 0 to a -4, because the 0 is undefined. So now I have a good set of points I can graph. Okay, I have 6 of them. I'm going to drag this over so that I'm able to graph it. So I'm going to plot those points. -2, -4, -1, -8, -4, -2. And then I'm going to graph the positive ones, 1, 8, 2, 4, and 4, 2. So what that's going to look like, it's going to be a curved shape that bends around the asymptotes. You see how it kind of bends to almost touch them but not really touch them. That's how your graph's going to look. And it doesn't have to be perfect. But visually, I want you to try to see if you can find any significance here. So let's talk a little bit about symmetry. We kind of get into this in higher math, not so much in this class. We talked about it a little bit. A graph has even symmetry if it's reflected evenly over the x-axis. Okay, so we call this direct symmetry. So for example, if you think of the quadratic parent function, this graph has direct symmetry. Because if I were to reflect it over the y-axis, it looks the same. Does this graph have direct symmetry?
Yeah.
Not direct.
Oh, not direct.
But it has some type. Can you all see the visual symmetry that's happening here?
If you tilt it over, then yeah, it'd be symmetry.
This is what we call odd symmetry in math. And the reason for that is it has symmetry, but the symmetry is actually over this line right here. Do you see that? How if I were to reflect it over that line, it would look the same. Or another way to think about it is if you were to reflect it over the line or the y-axis, then the x-axis. So like this and then this. All right, so your graphs are always going to have a form of symmetry. Okay, odd symmetry. So always make sure they look like they are symmetric to make sure you're accurate. All right, so let's look at another one. First thing we're going to do is we're going to analyze the graph and describe the transformation. So, what do you all think so far about looking at this? When you get a chance to look at it, when you flip your page.
Tedious is all.
So there's two things happening to this graph. Can anybody tell me what the two things are? Based on looking at the graph? So I'll give you no vertical stretches. Vertical stretch would be if this number was changed, so there's something other than 1. But there's a vertical shift. We have a vertical shift, right? And the vertical shift is left 4, right? Everybody see why it's left 4? Because h is always backwards, right?
Yeah.
And then what's the other thing?
Decays to -2.
Decay, yeah. Which means we're going down 2, right?
Mm-hmm.
Does everybody see how I identified that? Okay.
Yeah.
All right, I'm just making sure. So, let's look at the horizontal asymptote, which is always y equals k. In this case, it's going to be
-2.
good, y equals -2. Vertical asymptote is where you take the denominator and set it equal to 0 to find it. X minus 4. Very good. Okay, everybody good with those two asymptotes? Now domain is always based on h, range is always based on k. So you take whatever h is and you use this format. Negative infinity to -4, remember h is always opposite sign. Union, -4 to positive infinity. And then what's the range going to be?
-2 to negative infinity to -2.
Yes.
And then -2 to infinity.
Any questions about that? Alright, so we're going to wait to find our intercepts. We're going to look at the graph to do that. But what is my end behavior going to be on both of these? It's always going to whatever k is, which is?
-2.
So any questions on the analysis we have so far? Alright, first thing I'm going to do is I'm going to scroll over and I'm going to graph both the horizontal and vertical asymptotes. I'm not always going to remember what they are because I can't see it all at once. So, y equals -2. Oops. And what's the x one? -4? Is that, yeah, okay. Any questions about that? So now we're going to go ahead and actually graph this. So I'm going to scroll over here just so I can see what the graph is for a minute. Y equals 1 divided by x plus 4 minus 2.
Can you go back to the graph real quick?
Oh, yeah, I'm going to go back. I just had to type this in on Desmos. So I typed it in, and then I'm also going to graph my two asymptotes. So it's going to look something like this. So first thing you're going to look for are what those intercepts are. So intercepts occur when we cross the x and y axis. So I can actually visually click on my graph and find those values, if they exist, of course. So everybody see how I identified those. I'm looking for what crosses the x and the y axis. And you're only ever going to cross the y axis once in any function, by the way. So any questions about that? So I'm just going to move this over for a minute so I can fill that in on the So this is going to be negative 3.5, comma 0. And this one's going to be 0, comma negative 1.75. So do you have any questions about that so far?
Can you say it real quick?
Yeah. Alright, we get to look at the graph now?
Yeah.
Okay. So I want to get some points that are going to be useful for me to graph. So I'm going to pull over my equation. I'm going to hit the table button right here. And I'm going to find some points that will be nice to graph. So 0 looks okay. Maybe if I try negative 3. So this is kind of like a little bit of a guessing game to see what points are going to be useful. You can graph these messier points if you want to. They're just going to be a little harder to be accurate about. So I try to pick some that are more useful. So these ones are over here. What would I want to put in for x to get some points over here? What should I don't have anything over here, so what should I put in for x?
Negative 4.
That'll work. Negative 4 is actually the asymptote, so that'll be undefined, right? Negative 5, good. Negative 5 will be good. What about maybe like negative 6?
Positive.
And then maybe we'll try negative 8. So those are going to give me a few points on the other side of the graph. You could also try negative 7. But I think negative 8 is a little easier to work with. Not negative 78. That's really not good. So now that I have a few points, I'm going to drag this over so we can go ahead and graph them. So on my table, I have negative 2, negative 1.5. I have 0, negative 1.75. I have negative 3, comma, negative 1. And then I have negative 5, negative 3, 1, 2, 3. Negative 6, negative 2.5. And then negative 8, negative 2 point, whatever that is. So now that I have a few points, I can see what my graph's going to look like. So you can see what's happening with its end behavior. Both sides of the graph are just going to get closer and closer to that asymptote. So this arrow kind of looks like it's pointing out. It's going straight down, by the way. Anyone have any questions about it? Okay. Let's try another one then. So before we graph anything, I'm going to tell you that there's 4 types of things happening in this transformation. Can anybody tell me what the first one is? I can't hear you.
Going up 4.
Up 4. Okay.
A vertical stretch of 2.
Good. Vertical stretch. I think both of you said that.
It goes left by 3.
Yep.
And a reflection.
Good. So does everybody see those 4 things happening?
Why is it a negative 2, for that? Because
So this is the same thing as this. Mathematically.
Then wouldn't it not be a reflection, then?
Well, the actual definition of the reflection is when the 2 is negative. So, because what happens is it comes out front when you type, when you do math, like if you have like -1/2, it's the same thing as -1/2.
Right, I understand that, but, so if we just write the -2 there, then we shouldn't have to write reflection on the side, because we've already accounted for that negative, right?
Oh, well yeah, you can either put it here or here. Either one's acceptable.
Right, so like when we're writing this stuff down, we have vertical stretch by -2.
Oh, no, this is just a dash.
Oh.
Sorry, does that what's throwing you off?
Yes.
The vertical stretch is independent of whether it's positive or negative. And then the negative or positive tells us if it's also then reflected. Does that make more sense?
Yes.
Okay, sorry, that was like, yeah, that notation could be a little tricky. I see what you were saying though. Good point. So as for horizontal asymptote, that's going to be y equals k, which is y equals,
4.
good. Vertical asymptote is always going to be where you set this denominator equal to 0, which is going to come out to be x equals -3. It's always going to be whatever that's flipped, okay? Domain is based on h, range is based on k, so it's just -infinity to -3, union -3 to positive infinity. And then range is just the same thing but with k. And then these are always based on k, so they're going to be what? 4. We're always approaching whatever that horizontal asymptote is on both sides of my graph. Okay? So, any questions about that? Alright, so now we're going to go ahead and graph it. So I'm just going to type this into my Desmos real quick before I change screens. So the reason I really want you to practice with me on the Desmos is because it's pretty easy to get to a point where you get confused about how to type this in. So I just want to make sure you're all proficient with typing everything in. It seems silly until we get to the test or something and then you guys say like, I don't know how to graph it. So you always want to be prepared. So this is what I end up with. Looks something like this. Okay, I have my 2 asymptotes that I graph. So let's look at the intercepts. You know, we have to find those intercepts, right? So I click where we cross the x and the y axis. Does everybody see how I identified those intercepts? Bless you. So we have an intercept at -2.5. My x-intercept's at -2.5, 0. And my y-intercept is at 3.333 repeating. What is 0.333 repeating as a fraction?
1/3.
1/3. So I'm going to write it as 3 1/3 instead of 0.333, which would also be, as an improper fraction, 10/3, right? 10 divided by 3. Okay. So now I'm going to go ahead and graph this. I'm going to first graph my 2 asymptotes. So I have one here, and I also have one right here. Now that I have those, I'm going to pull this back over so you can all see the table function. What's up?
I'm confused. I'm not sure I put it in Desmos right. It's y equals -2/x+3 and then +4.
Does yours look like this?
Yeah.
Then you did it right.
I did not get the same. Oh, I see. Okay.
Yeah, it will negative sign will come out in the front when you do it. That's just how it works. So you hit this table, and then I get some table values. So I want to find some that are the most useful to me. So this is all good and well for this side of the graph, but I have to put some of these lower values in to get this side of the graph, right? So maybe I try -4, I try -5, and maybe -6. That one's not so nice. So you can put in as many values as you want. You can be as tedious with it as you want to get points, and then it will highlight the point on the graph as well. So I'm just going to pull this over so that I can plot them. So to plot these is going to be at -2, -2. Or no, sorry, -2, 2. -2, 2. There we go. -1, 3. -4, 6. -5, 5. And -7, 4.5. That's like right here. And I'm going to get one value, more value on this side. 0. I'm going to put in 0. I'm going to put in 1. Let's see what happens. Oh, 3.5. 1, 3.5. So I just get enough until I get a general look at what my graph looks like, and then I can just connect these. So looking at this graph compared to the other two that we've graphed, what's the main big difference that you see here? There's something very unique about this one compared to the others.
It's the crossing between the x and the y's above the.
Yes. See how all the other ones were like on the top right and the bottom left?
Oh, yeah.
This one's the other way around. What do you think did that to it?
The
Because-
reflection.
The reflection, the negative, very good. So same type of symmetry, but it's over the opposite way. So that's what the reflection does. All right, so does everybody feel pretty good with the graphing?
No.
No?
I hate doing that.
Okay, well, if you don't like it, I can't help you with that. I mean, it actually is pretty useful in different
I
applications.
think it applies just
Like, I
to
guess if you have
plot.
like a multi, like an x, y, and z and all of that stuff, and you want to see where they all intersect, that's kind of useful, but like,
If you want to be an engineer, it's very useful.
yeah, I guess.
So I'm going to skip number 4. If you all feel good with number 4, feel free to graph it in Desmos if you want. But we're going to just do 5 and 6 because I want to make sure we address these problems as well. So it's pretty common that you'll be asked to write a reciprocal function. So they're always going to have to tell you what the parent of the function is if they want you to write one. So I'm going to have to I'm just going to write out what the general form is. So you all see that from the front page. This is just the general form of a reciprocal function. And I need to figure out what a, h, and k are to come up with the equation. So 7 units up is representative of what letter?
H.
Not H. K. 1 unit left is H, right? H is left, right. K is up, down. What is vertical stretch represented by? A. And then it's reflected, so my A is going to be negative. So we have 4 things going on we're going to put in. So it's going to be y equals. We determined my A is 2, but also it's negative, so -2. We determined that we're 1 unit left, which means that my h is going to end up being +1, because h is always opposite. Good. And then what about k?
7.
+7. So everybody see how we came up with that?
Yes.
Okay, you're definitely going to have some of those on the homework. And then the last type of question I'm going to ask you is, I might give you a graph and ask you to work backwards to find the equation. Now with that being said, every time I ask you to do this, I'm assuming the a is 1. I guess I could give you one where the a is -1, but does everybody see, why couldn't I give you like one where the a is -4? Would you be able to visually see that very easily?
Probably not.
That would be a much harder problem. But to figure out what h and k are is pretty easy because it's based on the asymptotes. So all you have to do is you have to find those asymptotes. So I want you to draw in where you think the vertical and horizontal asymptotes are, looking at it. Do you all see where they are?
It's -2 and -1.
Yes, very good.
Yeah.
So of course you have to be able to tell which is which. So this one of course is x equals -1 because it goes through the x value, and this one is y equals -2. So we know that this affects the k and this affects the h, right? X affects the h, y affects k. So we know that the general equation is y equals a over x minus h plus k. We already said the a is 1. Now the h is -1, but it's really going to be
A +1.
a +1, and then the k is just going to be minus 2. So that's how you can work backwards. And then if you're using Desmos and you want to make sure you're right, couldn't you just graph your equation and make sure it matches? I recommend that on tests and quizzes for sure. All right. So for